Okay, let's briefly recap what we learned last week. So last week we learned some components of the embedded system. First of all, in every embedded system, especially for communication systems, we have some underlying technology. In this particular case, we are talking about wireless technology like 2G, 3G, and 4G technologies. And in addition to those, we also have a hardware platform such as processors and memory and various peripherals. And also there are part of software like operating system and some embedded and application software running on top of it. Remember that we discussed some integers and fractional numbers. And these are 8 bits we have. We are talking about 8-bit data, right? 8-bit microprocessor. So we have an 8-bit container, right? We have 8-bit container, and so using these 8 bits, we want to represent a certain numbers. For example, integers. This is an example. If we have a 5 is a decimal number, right? If we convert the decimal number into the binary, then we know that it's going to be zeros and 101. That's a 5, right? And you know these things, right? How to convert from decimal to binary and how to change the binary to hexadecimal to decimal, right? You know how to do that, right? So these are how to read those. However, from microprocessor perspective, microprocessor doesn't know anything. How to read this, right? You can read this one into decimal number, or you can read the same thing into the hexadecimal number. If you read this one as a hexadecimal number, it's going to be like 05H. Okay, 05, because in your hexadecimal, you read 4 bits at the same time. These 4, 0, these 4, 5. Right? Let's pick another example. Let's say you have a 1 here. 00010101. Right? You have 8 bits like that. If you read these 8 bits with the decimal number,
19.
Yeah, it's going to be 19. 19? Yeah, 19, because this number is 16. No, it's not 19, right? 16 plus 5, it's going to be 21, right? So that's when you have a 10101, and if you read this one as a decimal, then it's going to be 21. But the same binary, if you read that as a hexadecimal, then it's going to be 15, right? 15H. But microprocessor doesn't know anything, whether it's 5 or 158, whether it's 21, 15H. That's how we read it. Okay, microprocessor, it's 8 bits, that's it. You know what I'm saying? From hardware, microprocessor perspective, they don't know how to read it. They have only 8 bits, and that's it. It's for us. Okay, we have to decide if we read these 8 bits with decimal, or if we read it as hexadecimal, or we just take it as a binary. We decide that. You see my points? Okay. So here, right? We have another number. In this case, it's like a 0101, 0101. So for microprocessor perspective, it's just 8 bits. That's it, okay? It's just a 0101, 0101. That's all I know, all the microprocessor know. But when we read this, there are many different ways to read it, okay? If we read this whole number as a decimal integer, then what's the value? If we read this as a binary, the decimal integer, this is going to be 1. We have 0. This is 4, 16, 60, 16, 64, right? So we add 64, 16, 4, 1. You add all that, that's going to be the value. If we read this one as a integer, right? However, we have the same binary, but if we want to read this one as a fractional number, and we decide that this is the boundary for integer part and fractional part, then we can read the same binary number, we can read it as this way. So it's for us how to read it. It can be this number, or it can be like 64 plus 16 plus 4 plus 1, or it can be some other number. Let's say if we want to read that as a hexadecimal number, integer, then this is going to be 55H. Okay? Microprocessor doesn't know anything about those. Okay? It's for us. We decide how to read this. Right? Yeah. And not only that, let's say we are talking about negative numbers also, right? So who said that this is negative number? We did that, we. Okay? Microprocessor doesn't know. Microprocessor doesn't know this is minus, this is negative, or this is positive. It doesn't know anything. Microprocessor only knows that this one has, this is called MSB, most significant bit. The first bit is the most significant bit. And the last bit is least significant bit. MSB, LSB. Okay? What microprocessor knows is that this number has 1, MSB 1, and this one is MSB 0. That's all microprocessor knows. Okay? Other than that, microprocessor doesn't know anything. But when we read this, right, we read that as a -5, and we read as a 5. Or sometimes we read this one as a -5, or sometimes if we read this one as a -5. Okay? If we use 2's complement, then we read it this one as a -5. But for some reason, if you want to use these numbers, right, sign magnitude, then you consider this one as a -5. So it's up to you. You see my point? Microprocessor doesn't know anything. Why microprocessor has only 8 bits. Okay, how to read it, it's up to you. So suppose we use a 2's complement integer, which is the most common way of reading the integer value, right? Then we have this much of range. Since we have 8 bits, right? And this is positive number, this is negative number, so we have this much of range. So out of these 8 bits, think about unsigned number. You know unsigned number? Unsigned means you only consider positive numbers, right? That's unsigned. If you're familiar with C code, right? Then you know what they mean, right? Unsigned and signed. Signed means that you have both signs, negative, positive. Unsigned means that you don't consider negative. You only have positive number. So therefore, if you have unsigned, then you have, in this case, what's the range? From 0 to, if you have all 1, right? If you have all 1, 1, 1, 1, 1, 1, 1, 1, 1, what's the value? 256. Okay, that's if you have all 1, right? Then it's a 2 to the 8 minus 1. So it's a 255. How do you know? Okay, then let's say we have 16 bits. Another example. We have 16 bits and we have all 1. 16 ones. What's the value? If you read that as an unsigned integer, that's going to be, that's the maximum value you have, right? You have all 1, that's the maximum. That's going to be 2 to the 16 minus 1. 2 to the power, 2 to the power 16 minus 1, right? Why is that? I mean, let's take a simple example here. This is what? 2 to the 8 minus 1. How do you know? I mean, the simple way is that this is 2 to the 0, 2 to the 1, something like this, right? So the last one is what? 2 to the 7. So here, it's like 2 to the 7 plus 2 to the 6, 5, 1, right? That's this one. But the easier way is that if you have this number, right? Let's do plus 1. Then what's going to be? then it's like 1, 0, 0, 0, 0, 0, right? What is this? This is like 2 to the 8. And you added plus 1, right? So now you subtract minus 1. That's going to be this value. So therefore, it's going to be 2 to the 8 minus 1, right? So that's the maximum number when you have unsigned. However, when you have, so unsigned number, again, unsigned or signed, it's up to you, okay? Microprocessor doesn't know. So here, if we read these 8 bits as unsigned, the range of the value would be 0 to the 2 to the 8 minus 1. That's the range. But if we use 2's complement integer and we allow negative numbers, this is the range from minus 128 to the positive 127, right? That's the range with the 2's complement integer. So we know all these things. So this is a picture we looked at last week. Some very brief block diagram. Okay, every microprocessor has ALU, arithmetic logic unit. What is this one? What is this block? Probably you learned some of this block in other class, right? Digital logic, digital design, or some of those classes, right? Sometimes a microprocessor do a calculation, like addition, multiplication, something like this, right? All those actual calculation is done inside the ALU. Okay, this is the block that you do actual calculation. Registers, we are going to talk about details on the register today. Registers are special memory, special buffer, if you like. Okay, special internal memory. We have I/O ports, interrupt circuits, clock and ROM, clock, and these are some of the interface to the external device. We have a ROM. Sometimes we call this one as instruction memory, because in ROM we always contain some instructions or your code. Code memory, instruction memory, program memory, that's all same thing. Okay? Basically that means you write your own program and download your program into here. So that's why we call this a program memory, code memory, instruction memory, same thing. There are also other type of memory called data memory. Okay? So data memory is where you store some temporary values. Whenever you do the calculation, right? Whenever you run your own program, there is always necessary to contain some of the temporary value into some of the memory. This is where you put your temporary memories. So therefore, in this memory has to be read-write, because you write some temporary memory and also read it, right? You frequently read-write. However, instruction, you typically just simply read. Okay? You just execute line by line and you read line by line from here, unless you change your code. If you change your code, then you compile it and download it here. Okay? That's not what I'm saying is write. That's not writing. That's a kind of that's a burning the ROM or coding. We call it downloading or burning the ROM. That's not write. Okay? When I say write, what that means is while you are running your program, sometimes you need to write a temporary value into memory. That's what I'm saying is writing, not downloading. Okay? So this one, you can download it, but once you download it, you never write. You just only read. But this one, you can read, write also, right? Because temporary memory goes to here. Temporary value goes to this memory. So this is a brief architecture of 8051. We're going to look at details today. Here's a brief list of components of 8051 microcontroller hardware. First of all, maybe we can briefly talk about what this means. Here it says microcontroller. But you know, this course name is a microprocessor. So what's the difference? We sometimes hear microprocessor. Sometimes you hear microcontroller. What's the difference? generally, you can say this is pretty same. Okay, generally the same. However, if you like, you can see a little bit of difference. So here's a difference. Let's say when you have a PC, your computer, right? We have Intel processor, right? Or AMD. That processor, we never call that as a controller. We always call that one as a processor. However, let's say, let's think about any embedded machine. Let's say in a home appliances, let's think about washing machine. Let's go to your home and see your washing machine. Inside the washing machine, you have some chip called a microcontroller. That one, you don't call that as a microprocessor. You call that as a microcontroller. So what's the difference between the washing machine and your PC? That's pretty much the difference. The difference is that your PC and your microprocessor inside your laptop or PC is originally for calculation, right? Microprocessor is for calculation or some of the operation, execution of your code. Okay, you have a lot of code, and out of this code, you do a lot of calculations, right? And complex some work, right? However, think about this dishing machine or washing machine, okay? Or some other TV, for example. You see TV. Do you think the washing machine do a lot of calculation? Or TV? No, right? However, what happened in that kind of application is that you need to have a microcontroller, and microcontroller is connected to many different things. For example, sometimes microcontroller is connected to the LCD screen. Or in the washing machine these days, you will see LCD screen, right? Like right now, water is coming, what's the temperature, things like this, right? There's a screen. And not only that, there's a lot of buttons, okay? Sometimes you hear some sound. When the washing is done, then maybe you hear music or whatever, right? And the TV, for example, you need to have a remote control. So there are a lot of controlling devices outside, okay? So microcontroller, the main job is to connect to other devices, LCD buttons or some other video input, something like this, right? It is connected to many others. So the main purpose of that microcontroller is to control all the others rather than calculation. But think about PC, our PC. Our PC, of course, is connected to the screen, monitor, but that's not the purpose of a microprocessor. We typically use our PC to do a lot of calculations, okay? So that's the purpose. So that's what. For human being, let's illustrate that as a human being. Microprocessor, like a processing capability, is same as your brain. So there are, maybe think about two different people. There are one people who is doing a lot of calculation in the home, in the brain, okay? There's one guy who is doing a lot of thinking, a lot of calculation, and use a lot of brain. That's like a microprocessor. There are another guy who doesn't use his brain, but hands is busy, okay? Doing a lot of things. That's like a microcontroller, okay? Same as like that. So the 8051 mostly is microcontroller. You do some calculations sometimes, but the main purpose is not really doing a lot of calculation. Rather, you want to use this one to do a lot of controlling capability, okay? So that's why people typically call this one as a microcontroller. Okay, your book says microprocessor, but pretty much the same. However, there's a slight difference. Okay, it's more microcontroller. Okay, you may want to understand the difference. So let's see some of the components. We have an internal ROM. This one. Okay, internal basically means that this memory is inside the chip. That's what that means, internal. You see there are different numbers, right? 8751, 8031, 8051. These numbers are the different chip. However, you see those are pretty similar, right? 8051, 31, 8751, all those are the same family. Same family. So this is maybe the the first generation, and later, if some people want a little bit low-cost chip, they remove internal ROM, they remove it and make a little bit cheaper version. But other than no internal ROM, all the other things are same. Okay? So difference between this one and this one is that this one has 4K size of internal ROM, but this one has no ROM. That's the only difference. All the others are the same. So those are the same family. Okay? Similarly, this one is another family. Only difference between this one and the others is that this one, 8751, we have EPROM. What is EPROM? Erasable. Erasable ROM. Okay? Erasable. E means erasable. Erasable programming. That's EP. Typically, ROM is not really it's not easy to program it, but this one is a special ROM which allows you to erase and program it a little bit easily. So there is 8751. Okay? Other than this one, all the other things are exactly same. So that's why we call that as a family. There's another one, actually, I didn't list it here, but there are another number which has flash memory as internal ROM. You know, flash memory is actually better. These days we have a flash memory, right? But right now here, 8051, this 8051 processor, 8-bit processor, is like 40 years old, right? As I discussed in the last week, we looked at the history, right? This one appeared maybe 30, 40 years ago. So when going back to 30, 40 years ago, there was no flash at that time, right? So at that time, you have this much of internal ROM and sometimes no ROM or things like that. But these days, we have a flash. So instead of these things, we have a flash. So that's another number. That's also still same family, right? But that's another one. So we have internal ROM, or sometimes no internal ROM. Okay. 8051, we also have internal RAM. What is internal RAM? This one, right? We call that as a data memory. This is where you contain some of the temporary memory, read-write. Generally, in 8051, you have only 256 bytes. So tiny, right? From our perspective, it's so tiny. But think about this one as like 30, 40 years ago. It was pretty good size at that time, right? So it was internal RAM. This is a little bit detail. There are another version called 8052. Okay, again, it's the same family. There are so many different families. 8052 has double of this, 512 bytes of internal RAM. That's 8052. Okay, a little bit advanced version in this family. So there are a lot of variations. So this is our internal RAM. We have this much. We'll look at details about this one next slide. There are a lot of registers in 8051. This one also we look at it detailed next slide. But the most important thing is that you need to remember the name of the registers. Okay. First one, the most basic and important thing is register A. A means accumulator. All of the microprocessor pretty much has this register. If you look at the Intel processor, they have their own name for registers. Okay? If you look at the, let's say, Texas Instrument processor, they name their own registers differently. Each processor has its own name for registers. But pretty much, accumulator is common. For every single microprocessor you see, you probably see the accumulator everywhere. Most basic one, accumulator. We call that as A. Just make it short as A. In 8051, there's another one called B. That's another register. These registers are 8-bit registers, 8-bit. There are also 16-bit size registers. This is a size, right? A, B, its size, their size are 8 bits. But there are another registers called the program counter, which make it short as a PC, and data pointer. And those two registers have a 16-bit size. Okay, I'll give you a reason why. You need to understand why. Otherwise, you don't want to remember these things, right? It's not important to remember. Nothing to remember. But what you want to know is that you want to understand why. Why this one is a different size. Other than this one, right? Other than PC and DPTR, all the other things are 8 bits. Let's go to this one. We have a register called the PSW, Program Status Word. Okay? That's another register, but that's also 8-bit. We have a very important register called the stack pointer. That's also 8-bit. All of them pretty much 8-bit. We have also another register called the P0 to P3. So P0, P1, P2, P3. We have 4 of them. And each of them is again 8-bit. Okay? And timer, this is timer register T0, T1. We have 2 different timers. Okay? We learned the timers maybe a couple of weeks later. But this one has a 16-bit. There's a reason why. Okay? You want to understand that. Serial port, and there are some special control registers like this. Okay? Some of these things. We look at those details. Okay? Those are the registers we have. There are a lot of different types of registers. Okay? And also, in 8051 hardware, we have 2 external and 3 internal interrupt sources. Okay? Interrupt is a very important concept. Very, very important. We're going to study this one maybe after midterm or something. But interrupt is very important. You want to understand this one. Okay? We'll cover that later. And oscillator clock circuits. That's necessary for every digital systems. Let's move to the next slide. This is the organization of internal RAM. In the previous slide, we looked at, we said that we see that the internal RAM is 256 bytes. Okay, 256 bytes of internal RAM. This is 256 bytes. How do you know? How do you know this is a 256 bytes?
There's session chambers.
There's what?
7 cells, 1, 2, 5, 6, 7.
Yeah, there's an address here, right? From 002, FF. What is FF? 1111, 1111, which is?
Hexadecimal.
Yeah, this is hexadecimal. This is 1111, 8 ones. So that's going to be in decimal number. This is going to be 2 to the 8 minus 1, which is 255. So we start from 0 to 255. So that's whole thing is a 256 bytes, right? So we have 256 bytes of internal RAM. In this 256 bytes, they actually divide it into different parts for different purpose. So down here, we have a small 4 part. This one, this one, this one, this one, right? Right? And each one is 8 bytes. 8 bytes, another 8, another 8, another 8. Okay? And each byte, each part does like this one, right? Each one is called bank. This bank. What is bank? In English, you know, bank. Bank, you know, where you put the money, right? Or you withdraw some money out of bank. However, in our area, like in electrical engineering, we use bank in a different context. Have you heard bank in other context? Generally in bank, in our technical area, bank means multiple of them. That's bank. So for example, let's say you have, in this particular case, right? This is a bank 0, so you have a multiple of these, right? Same thing, here, 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 here. Okay? So that's a bank. So this is bank 0, bank 1, bank 2, bank 3. You often hear bank in like a filter. You probably didn't learn the DSP yet. Next semester, you probably learn DSP, right? When you learn the DSP, you probably learn filters. You know filters, right? Low pass filter, things like that. In some of the applications, you use a filter bank. What is a filter bank? Filter bank is like you have multiple filters next to each other. That's a filter bank. Okay, so bank means you have something, but not just one, but you have a multiple next to each other. That's a bank. Okay, so in this case, it's like a memory bank. You have a bank 0, bank 1, bank 2, bank 3. So this one is a one bank. You have a multiple of them. In this case, 4 of them. So we call it as a bank 0. In bank, each bank, you have registers called R0 to R7. We have 8 bytes. We have 8 bytes here. And in bank 1, we also have R0 to R7. Same thing here also. In here, bank 2, you also have same thing, R0 to R7. Bank 3, same. Okay? So you have same thing 4 times. Each one has a different bank. Then how do you know? This one has R0. This bank also has R0, R0, R0. We have 4 R0s, right? How can you differentiate? Each one is a different bank. So right here, you see the 2 bits, right? Bank 0 is like a 0, 0. Bank 1, 0, 1, right? Here, see, bank select bits in PSW. What was PSW? Go to the previous slide. You see that PSW is program status word. So you have one register, 8-bit register called a program status word. And inside, if you look at that 8-bit register, PSW register, then there are 2 bits in there. Okay? There are 2 bits inside the PSW, and those 2 bits are called the bank select. Okay? So you first set those 2 bits. Like I say, in that 2 bits in PSW, I write it as a 0, 0. Then what that means, I want to select this one. Okay? If you write those 2 as a 1, 0, that means I'm going to use this bank. Okay? You're going to use those 2 bits to select your own bank. Okay? So you have 4 of them. This part, like a 20 to 2FH, how much of this size? 16, yes, 16, right? 16 bytes. This 16 bytes is called the bit addressable space. So what does this mean? This is like a very special area for 8051. So it sounds like you have a bit addressable space. Generally, right? What is address, by the way? Address. This is address. 00 to FF. Right? This is address. But each address is 4 byte. Okay? This is a byte address. You have an address 00. That means you have a 1 byte with a 00. If you increment the address to 01, then it's next byte. Okay? It's byte by byte address. You cannot do the bit addressing. Generally, in microprocessor, bit addressing is not possible, right? You see what I'm saying? So byte is 8 bits, right? Let's say you have address 10H. This one, right? When you say address 10H, that basically means that you want to have this byte, 10H. Okay? You cannot say that, okay, I want to access only 1 bit here inside this byte. That's not possible. If you really want to do that, then what you need to do is that you first read this whole byte, because this whole byte is 10H, right? So you use this address, 10H, and you read the whole byte, and then you take only that byte later. Okay? That one you can do it. However, from microprocessor perspective, you cannot simply only read 1 byte. It's not possible generally, because address is associated with a byte. However, this part, you can do that. That's what that means. you can do the bit addressable space. You can only read only one bit in this space, only one bit. That's what they mean, okay? Bit addressable space. This part is 30H to 7FH. This part is called general purpose, which means you can use this space whatever you want. General purpose. If you want to use it, you are free to do it, okay? From 80H to FFH, in fact, this is half of the whole thing. Whole thing is a 256. This one is the half, 128 bytes, right? This area is called the special function register. This area looks like this. This is 120H. We have 80, address 80 to the FF. So we have 80 here up to FF. Okay, FF. Okay, so this is a whole map of this area. This is special function register area. Now this is address. As I said, each address is for byte. Okay, each address is for byte, right? But in this case, see here, this is a byte, another byte, another byte, and you see that these names, right? What are those names? Those are the names of the registers, okay? So going back to overview diagram, we have a registers, right? And what kind of registers we have? We have these registers, okay? We have these many different registers. And where are those registers? They are here, actually, right? They are actually here. So we're going to learn one by one later, but let's see briefly. P means a port, okay? What is port? Port means input port, output port. Look at this picture of the, general architecture. We have a port 0, port 1, right? Port 2, port 3. So this port is like an interface between the chip, between microprocessor and the outside. Okay? So why do you need port? You want to connect it to it. As I said, this is microcontroller. So what do you want to do? You want to connect this one with LCD. Or maybe you want to connect this one with the buttons. Okay? So you want to control all these devices. So LCD, you can put it here if you like. It's up to you. How to design it is up to you. You can connect the LCD in this port. And if you like, you can connect the buttons in this port. Okay? You can connect this one whatever you want. Okay? So these are the ports that you can connect to the external devices. So that's a port. Sometimes you can use this port as an input device. Let's say I want to connect to a camera. Okay? Like a video webcam type of thing. So you connect webcam here. But typically webcam is like the camera is only capturing the scene, right? Capturing the pictures and send it to the processor, right? It's not like this way, right? Think about it, right? The camera is like from microprocessor perspective, camera is like input device. Camera is only giving the input to this way, right? Whereas LCD, pretty much LCD is an output device, right? You want to display something, then you send it over, and LCD will display it. Generally, LCD does not give the input. Okay, so some of the devices are input device, some other devices are output device, like a mouse. Think about your PC. Mouse is an input device for PC, whereas a printer is output device, right? Each device has a different type. You can set each port as a different type. You can set this one as an input port, or you can set this one as an output port, or you can set this on output port. You can set each of them as an input or output, whatever you want. Okay? That's why we call it as a general purpose input output, GPIO. You will hear GPIO many times, many times. Typically we short it as a GPIO. GPIO means general purpose input output. Okay? Meaning you can set as an input or you can set as output or both directions, whatever you want. Okay? So those are the ports. In 8051 we have 4 different ports, 4 ports, right? So therefore we need 4 registers, P0 to P3. Okay? Then why do you need port? Why do you need register for each port? This P0 is the register for port 0, right? P1 is the register for port 1. So why do you need P0, P1, P2, P3? Simply think about it. Why do you need the register? We already have a hardware. We already have a port hardware. So what do you need for this? Controlling what? Such as what? Yeah, exactly. That's what I said, right? I just said that you can use a port 0 as an input or output. Okay? But you have to say here, okay, I'm going to use port 0 as an input. In that case, maybe you say it's all 0. I want to use the port 0 as an output. Then maybe you write all 1. I'm just giving you an example, okay? So that's the purpose of these port registers. Let's think about another one. SP, stack pointer. What is a stack? So we'll look at stack in the next slide. That's very important. Stack is very, very important. Okay, we'll look at it. There are all other registers. You have in this case, right? You see that DPL, DPH. Low, L means low, H means high, which means these two are same thing, basically same thing. Remember that we have 16-bit registers. What was 16-bit registers? Let's go back here. We have a register called a program counter and also data pointer. That's a 16-bit, right? But here, as you see, everything is a byte. So therefore, you need to have 2 bytes for DP, data pointer. Basically, data pointer is 16 bits, so you need 2 of them. And put together, make it 16. Okay? So that's why we call it LH. There are some other things, but we'll look at those details a little bit later. There are some registers for interrupt. Okay, accumulator. This is A accumulator. We have a B also. Then now you may want to ask question, what is this gray area? All this area. What is this? Huh? This is unused area. You are wasting. I don't know why they're wasting, but I think maybe going back to 30, 40 years ago, when the designers are designing this 8051 processor, they probably think that, okay, this area right now is unused, but later they may want to use it. So it's like a future purpose. When you design hardware, right, sometimes you need to have such space. Right now I'm not using it, but later I want to use it, right? So there are a lot of places like that. Every hardware has such things. This part is something like that. Okay, they leave it as unused, but they have a plan. They had a plan to use it later, but something happens in the meantime, so maybe they didn't use it later. But anyway, right now in 8051, they are not using this area, which means since these areas are not used, for some reason, if you want to access this area, let's say I want to read this address, then what happened? This area, memory is not defined, unused area. So if your processor is trying to access, trying to read, or trying to write some value into undefined area, then what happened? Who's going to reply there's nothing? Of course, you have an error, right? Of course. Maybe you have some experience of programming when you write a C program, right? then you compile it and you run it, and suddenly the program does not run, and you see some of the error. For example, like some exceptions or stack. What's the error? There's an error called the stack something, right? So there are some exception. Exception means that program cannot run, so it's just down. The program is down. Okay. When you run the program and suddenly the program downs and nothing work. Okay. Typically, the reason is that you are trying to access undefined area. Okay, so that's very bad. You should not do it. The program is down if you do it. So this is a general overview of internal RAM. We'll look at the registers detail in a couple of slides later. Memory address space. What is this concept? It says memory address space. So this is a memory address space for internal RAM. This is the whole memory map of a program memory. Remember that we know that there is a program memory or code memory or instruction memory, and there are another type of memory called the data memory, right? We have two different types of memory. And each memory has a memory space. What is a memory space? Memory space means address. So this one has address from 0000H to FFFF. So from this one, now what you can see? How much is this space? Let's say this is a whole memory space, right? Whole code or instruction memory space. How much is it? It's a 2 to the 16 minus 1. How much is a 2 to the 16 minus 1? Let me ask a simple question. Like you, these days, right? You have like 4 gigabytes of memory. How much is 4 gig? 4 gig is what? 2 to the? How much? Huh? 16? 34? Why 34? 1K, 1 kilo is 2 to the 10. 1 meg, 2 to the 20. Yes. 1 gig, 2 to the 30. 4 gig is 2 to the 32. Right? Here we have how much? How many bits? 16 bits. 1111, 1111, like this, right? 16 bits. So therefore, the total space is like 2 to the 16 minus 1. 0 to the 2 to the 16 minus 1, right? We start from 0 all the way to the 2 to the 16 minus 1. So this whole size is 2 to the 16, which is 64K, right? Because 2 to the 16 is the same as 2 to the 10 times 2 to the 6. This is 1K. This is 64. So therefore, 64K, right? So 64K is the total size of your address space. We have an address space of 64K, right? 64K. What is address, by the way? Here's the same easy illustration. Let's think about in our campus. Okay, in our campus, we have so many buildings, like this building and another building, and we have so many different buildings. And each building has a different address. Okay? Actually, in our campus, we have a different name, like engineering building 1, 2. But maybe let's go outside, not campus, forget campus. Let's go outside and let's go certain area. We have a lot of houses here, and each one has a different address. This house has address 100. Next house, 101, 102, things like that, right? Why do we have such kind of address?
Because there are lots of houses, we need to distinguish. Like
why do you want to distinguish? What's the purpose of doing distinguish? Let's say you have a postman, okay, mailman, okay. I want to deliver a letter, okay, something like this, right? then I need to know the address, and address has to be different for each house, right? Only that way I can access. Same way, and each of you has a different name, right? Of course, there are some exceptions, but generally each one has a different name. Only that way I can call the name, and I can distinguish each of you. Same here. This is a memory space. I want to access byte by byte, and every byte has to have a different address. Only then I can access each one differently, right? I want to access this particular byte, then I give the address of that. That way I access this byte. I want to access another byte. I have to use another different address, right? That's the purpose. Now then, this size, 64K, this is the total number of bytes we have in this 8051 processor. Okay? This is the total number of address. Okay? Now then, we'll look at that detail. But anyway, we have a 64K byte of address space. That's called the address space. This much is the available address. So here's an illustration. Let's going back to our town. This is our town. We have a house with the address 100, 101, 102, things like that, right? And right now in this town, we have only 100 houses. So from 100, 101, 102, up to 200. Okay? But I'm basically a planner of the whole city, whole town, and there are a lot of other area, and we have a plan to build more houses. Okay, right now we have only 100 houses, but we want to build more. In that case, you have to reserve other addresses, right? We only have 100 to 200, but later we build more houses. We're gonna put the address like 201, 202, 203 later, right? Right now we should not use that address because later we're gonna use it. You see what I'm saying? Right now we don't have the house. Same thing here. We have a 64K of address space. That doesn't mean that you have to use all of them. Maybe this is an address space, available address space. Maybe you buy a memory, small memory, and this memory has a size of 4K. You can buy a 4K memory. Okay, only 4K. And those 4K, you can put it here. Maybe this from here to here, so let's say 4K. You can put it here, or you can put it here. In that case, from here to here, 4K space, you actually map your actual memory into this address space, and the other 12K, you are not using it. Okay? Right now, you are not using it. But later, if you want, you buy another memory, second memory, another 4K, and put it 4K more. In that case, you have two different memories. Each one is 4K, total 8K. Okay? You're going to use 8K. Again, even in that case, the other 8K still it's empty. So that's possible. You see what I'm saying? So address space doesn't necessarily mean that these are all the memory you are using. This is just a space you can use later. Same here. I have this much of town. Okay? That doesn't mean that you have all the houses. We have this much of town, but out of this town, maybe you have only this much house. All the other place, maybe later we can build more houses. But right now we don't. We don't have it. Same thing. Okay? So now you need to understand the difference between the memory address space and actual memory. This is not actual memory. You see my point? In my illustration, okay, this is the size of the town. That's the same as address space. But how many houses you actually have? I have only 100 houses right now. That's actual memory. You only have this much of memory, but you can have this much of space. Same here. Okay? This is a memory space, but you may be using only this much of actual memory. Okay? Same here. In external memory, that's a data memory. This is a memory space, not the actual memory. And out of this memory space, you can actually use some of the address space with some actual memory. You can put the actual memory here. If you buy a 4K memory, then you put it here, use 4K. Or if you buy only 1K memory, then you put it here, you are using only 1K. But address space is still there, this much. Okay? This program code memory, inside this program code memory, this internal RAM from 00 to FF, this one goes here. Because we have a 00 to FF, right? It goes here, 00 to FF. Okay? So this one, it's like this, right? Going back to my town example, I have a town, this much of town, I have 100 houses. Okay? But since this is town, I have a city hall. I have some building for some public work, something like this, right? So that building, we give a special address. Like this building, we have a address 1. Okay? This one has address 1 because this is a very public special building. All the other buildings is like a house. So your house maybe have a address 70. His house 75, something like this. But this special building, everyone use this building, right? It's a public building. This building, I give a special address like 1. Same here. This is a very special area, special memory. So that's why for this memory, I give a special address area from 0 to FF and map it here. Which means that you are not going to use this one as your plan. This is already mapped. So if you buy another memory, additional memory, then you don't want to put it here, right? Because this address space is already used, right? You don't want to map it here because this address space is already used with this purpose. Okay? Same here in town. This public building has address 1. Let's say you buy another one house here. Do you want to make the same address? No, right? You want to avoid this address. You want to have another address number. Same, okay? All the other address space you can use if you like. Let's look at a little bit more detail about the registers. Let's say 34 general purpose registers. Why 34? Because we have 4 banks, and each bank has 8 registers from R0 to R7. Remember? Going back to this. Each bank, we have 4 banks. Each bank has register R0 to R7. We have 8 register each bank. So therefore, we have a 32 different registers. And we have accumulator. Also, we have a B registers. So we have a 32 plus A, B. So we have a 34 general purpose registers. General purpose means that you can use these registers whatever you want. Any purpose. Okay? So we have these many registers. There are special function registers. These are general purpose, but these are special functions. So these registers you have to know. You have to understand very clearly. First, stack pointer. We look at next slide. Program status word, program counter, data pointer, and these things. So let's look at one by one. So this one, we don't have to talk about details. The only thing you need to know is that each one is 8-bit. Okay? 8-bit. And this is general purpose register. You can use whatever you want. Okay? So that's it. Yeah, let's look at the program status word first. This is the program status word, one of the registers. You see that it says a status. What that means is this register is a very special register which tells you the status of the processor. Status of the processor. So here's the thing. Let's say For human being, right? Status means a condition, my condition. Okay, I'm sick, something like this, right? I'm happy, something like this. So that's status. For human being, maybe it's not a good example. But here, I'm saying that there is a register called the program status word. And in this register, we have so many different bits. And if we want to understand what is the status of this chip, okay, what's the condition of this chip, we want to read, we want to look at each of the bits. Then we understand what's the condition, what's the status. So let's see one by one. First of all, CY. And each of that is called a flag. Flag. What is flag? Flag. Okay, that's flag. Why do we call each of them as a flag? Because each bit is a different condition, okay, different status. And each bit is just binary, either 0 or 1. 0 or 1 means the same as flag. 1, 0. 1, 0, like this, right? We call that a flag. First one is called the carry flag. Then now we need to know what is carry. You learned carry, right? In other course? Carry. Okay, we will look at it here. And the second bit is auxiliary carry, the similar one. F0, user flag. Actually, this is not used. So right now you can forget this. RS1, RS2, what is this one? Bank select. We talked about bank select, right? So using these two bits, now you select the bank. We have 4 banks, right? From 0, 0 to the 1, 1. So you are going to set these 2 bits, like 0, 0 or 0, 1, 1, 0, 1, 1. So therefore, you select the bank. So these 2, we call as a bank select. This one, overflow bank, overflow flag. Now we need to know overflow flag also, right? Overflow means. Last one, parity flag. So important thing here right now is that this one, carry flag, auxiliary carry, overflow, parity. These 4 bits you need to know. Okay? Last year and 2 years ago, when I taught this course, I always have this problem, this question in the midterm and quiz. And I'm going to do the same thing. But pretty much there are a lot of students who does not distinguish these things. So you want to understand it clearly. So this is the example. So let's see what it is. First of all, what is carry? Let's see one by one. Carry. What is carry?
1, 1, go
1, 1, 1, 1, go 1. Okay, yeah. That's exactly right. So look at here. 1, 1, go 1. Yeah. Look at here. This is where when carry flag happens. So we have 2 different numbers. And each number is 8-bit, right? Because all of the other registers are 8-bit registers. So now we, in one register, let's say this is R0. And this is, let's say, R1. Because those are the general purpose registers. Let's say we have this value in one register and another value in second register. And let's do addition. Okay? We're going to do the addition. This is the output. You can do the binary addition, right? Just simply add the binary, 2 different binary numbers. This is the addition, result of the addition. So now you see that since these 2 numbers are 2 big numbers, think about this as unsigned, okay, right now. These are two big numbers. When you add these 2, now you have 1 outside here. What happens if this happens? This 1 is gone. Why? This one disappears. Why? Because our register is 8-bit. We only have 8-bit container. Okay? So this one disappears. Suddenly disappears. But it is disappearing from register. But instead, what happened? if this happens, then the output register will only have this number. And because of this, now we have carrier flag 1. Okay? If this happens, this one becomes 1. Generally, in normal situation, this is 0, right? Only when this happens, this becomes 1. Because what that means is we have a carry now. This is a carry. Okay? So this flag goes 1. So what does that mean? What that means is when you do the addition, especially when you have a big numbers, right? Whenever you do the addition, first thing to do is that you have to check carrier flag, right? You see my point? Because if you, in generally, right, you add two different numbers and the output goes to this register, right? And simply, we read this value, then that value should be this plus this. That is only true when these two numbers are small, but these two numbers are big. Then this value actually becomes smaller. So let's see why. It's pretty easy to understand, but let's say we want to do, let's think about unsigned numbers, just for easy understanding. Let's say we have, let's say I want to do this addition, okay? And I put this number into A, and this number into B, okay? And I do this one. This is the registers, right? And the result would be this one. Okay, I'm expecting this value, right? I'm expecting this value. And typically when you do this in assembly language, when you add these two, the result goes to A, okay? So now A value is changed. You have A, B with this value, but when you add it, the result goes back to A. So I'm expecting A equal to this value. That's what I'm expecting. However, if you do this, what is the value actually you see? You don't see this value, right? What value do you see? Think about unsigned. Okay, now then we have to go back to that one, right? So let's say we have 8 bits. What is the range, what is the range of the value you can have? 0 to? This is the maximum number you have, right? You cannot have this number with 8 bits. Okay? This is beyond my range. I can only have these numbers. So now let's see. I want to have 280. Then how can you do it? And what happened in the microprocessor? Huh? Yeah, well, yeah, of course, the carry flag will be on. Carry flag will be set. But I'm saying that addition to the carry flag, what value do you have in A? Let's say my output is 256. Still, the 256 is higher than 255. So what value do you have? If you have the result of 256, why? Why 1?
First, number 1 is gone.
Because carry flag means that 2 big 1, and the rest of them need to be disqualified.
Okay, then why 1? Should be 0, right? So here's the thing. Let's say you have a 0, 1, 2, all the way, 255, and next thing is 256, right? 256 is like going back. So this is going to be 256, 257. Think about it, 257, 256, what is this? It's like 1, 0, 0, 0, 0, 0, 0, 0, 0. So this is dropped. And because this is dropped, and this dropped bit is 1, now we have a carry flag. And the other thing will still there. Okay? So if you have the result of 256, the result, you have 0, not 256. You have 0. That doesn't make sense, right? You add two of them and the result is supposed to be 256, but instead of 256, you have 0. So that's why you have to check the flag. If the flag is on, now then it's 256. Same thing here, right? Let's say in this example, let's say you have a 280, but 280 is higher than 255, right? So in this case, what happened is now you have a carry flag on, carry flag is set, and the remaining value in A is 280 minus 256, right? 24. Is it 24? Yeah, you have a 24 here in A. Okay, that's the result. Okay, this is carry. This is what happened in microprocessor. And when this happens, you have a carry flag. Now let's see auxiliary carry. This is AC. In fact, AC is not important because AC probably is needed maybe 30, 40 years ago, but these days nobody uses AC because AC, look at this picture. This is a carry flag. Now let's see auxiliary carry flag. In this case, it's exactly the same as a carry flag. The only difference is that auxiliary carry flag is on when 4 bits, when you add the 4 bits. Let's say you add these 4 bits, right? 4 bits. And when you add these 4 bits, now the result becomes 5 bits. Okay? Same thing happens, right? We have a 4 bits plus 4 bits, but the result becomes 5 bits. So there's 1 bit going up. Okay? There's 1 bit going from this bit to that bit. That's auxiliary carry. So this flag was needed when they look at 4-bit register. Okay? So this, when 30, 40 years ago, right? This one was 8-bit register, but at that time, there were a lot of 4-bit processors. So 8-bit was pretty good at that time. So therefore, you want to make a compatibility with 4 bits. So therefore, they introduced the auxiliary carry, but I think nobody uses these days.
And why there is auxiliary carry?
Why do we have this? I think this one is still there. It was designed like 30, 40 years ago, but it's still there. So at that time, like 40, 30 years ago, they probably need this because at that time, 8-bit is a really big number, and sometimes they have to deal with the 4 bits. So therefore, auxiliary carry may be necessary at that time. But these days, nobody uses it. We already have a 32-bit microprocessor, things like that. 4-bit, who cares? We don't use 4-bit. But anyway, the concept is same. Okay, carry flag, auxiliary carry, same thing. Only difference is that carry flag happens when you add 8 bits, add 2 different 8 bits, and the result becomes 9-bit. Then carry flag is set. Auxiliary carry flag is on when you have 4 bits, 4-bit plus 4-bit, and result becomes 5 bits. Then auxiliary carry is on. Now then, question here. Let's say the same example here. Okay, I'm going to add these two, and the output is this one, right? So as you see here, we have adding these two, so now we have carry flag is on because of this, right? Because of this, we have now carry flag. Okay? What about auxiliary carry? Auxiliary carry is also on. Okay? In this case, CY, the carry flag is 1, and also auxiliary carry is also 1. So these two are independent, okay? Sometimes you can have both bits 1, 1. Sometimes. In this case, why? Because you have a 1 here, okay? You have like an auxiliary carry, right? That's the condition of auxiliary carry. So what I'm saying is that sometimes these two becomes 1, 1. Okay? So think about the condition. Okay, think about the condition. These two are completely independent. Okay? Both can be 1 at the same time. So now let's see. What is this one? What is this one? Overflow. What is overflow? This is a condition where you see overflow flag. This is overflow. Why is this overflow? What is overflow? Overflow condition happens when you think about signed integer. So let's see here. Let's consider that as a signed integer. This is a positive number. You see this is 0, right? This is positive numbers. Another positive numbers. But when you add two different positive numbers, for example, right? Let's see example. Let's say I have a number 64. Let's say I have a number 71. So I'm going to add. Then output is going to be this one. But now think about the signed integer. What's the range of the signed integer? 2's complement. Think about 2's complement. What's the range? This is the range of 2's complement numbers, right? We don't have this. So what happened? If this happens, microprocessor will, again, when you have 228, it's go back. It's go back up like this. So therefore, when you do this addition, and this is A, this is B, and when you do addition, the result goes back to A. A does not have this value. A have what value? Minus some value. So go back, okay? You have some minus some value. How do you know? See the result here, right? When you do the binary addition, this is the output, okay? But this output actually is negative number. This is actually a negative number, right? So you are adding two different positive number, right? And you go back, it's rolled back. It's rolled back and it becomes negative number because it overflowed. That's overflow. You need to see the difference between overflow and carry flag. And auxiliary carry pretty much easy to understand, but carry flag, overflow flag, sometimes it's like tricky, okay? So you may want to do a practice, okay? As I said, it's a part of your quiz or possibly midterm.
And carry flag is for unsigned number and overflow flag is for signed number.
That's a very good question. What's the answer for that? No, right? Because as I said, the microprocessor doesn't know anything. Microprocessor doesn't know whether this is a signed or unsigned or hexa number, decimal number. Microprocessor don't care. So what it is that this condition is pretty clear, right? Microprocessor only have 8 bits, but the output becomes 9 bits. So it's pretty clear. We should have carry. In this case, signed, unsigned, doesn't matter. Okay? It doesn't matter. Because we have 8 bits, but the result becomes 9 bits, so we have carry. Think about now overflow. In this case, 8 bits plus 8 bits, again is 8 bits. No problem, right? However, look at the first bit, called MSB, most significant bit. Both of them was 0, but now the output becomes 1. That's the condition of overflow. The reason that I said this is signed or unsigned, those things is like I explain that way because that's easy to understand. Okay, for you it's easy to understand, but microprocessor doesn't know anything. Sign, in-sign, very simple. Okay, for microprocessor, very simple. 0, 0, but output is 1. The first bit, right? MSB, both are 0, but output is 1. Overflow. Very simple. And you are adding two different numbers, and the output becomes 9 bits. Carry. Okay, it's very simple.
By the way, how can you calculate the remaining?
Remaining.
I mean, when we do a carry flag, it ranges from 0 to 255, but overflow flag, we arrange them minus 128.
Okay, good question. This is pretty much the same question. As I said, microprocessor doesn't know this number, right? Microprocessor give you this number. And when we read it, okay, when we read it, if you want to have this one as an integer, the unsigned integer, maybe then you can have this number. Okay, because I said this is your choice. I want to read each of them as unsigned, then the last one is this number, right? Because I said it's unsigned, the range is from 0 to 255, unsigned. So this value becomes 135. But with the same value, if I read each of them as each one has a signed integer, okay? I want to read it as a signed. In that case, the same bits, this one, becomes minus 30, minus some value, right? Because I read that as signed. Okay? So if you want, then you can read it as unsigned. Or if you want, you can read it as a signed. Okay? If you read that as unsigned, that value becomes 135. If you read that as a signed, it becomes minus some value. It's up to you how to read it. However, microprocessor doesn't know. Microprocessor simply the MSB 0, 0, and you add 0, 0, but output becomes 1, overflow. They don't care. Unsigned, signed. Okay? Think from the microprocessor perspective. Microprocessor is very dumb, very simple. Okay? Very simple. Okay, when you read it, if you want signed or if you want unsigned, it's up to you.
So what they do is just calculation, but just like what we read is ourselves.
Calculation, yeah, calculation is simply binary calculation in this case, right? In order to do the binary addition, you don't have to say that, okay, I'm going to use a sign or unsigned. Whether it's a sign or unsigned, binary addition is same, right? You don't care. Binary addition is simply 1, 1 becomes 1, 0, right? 0, 0, you add 0, 0 becomes 0. 0, 1 becomes 1, 0. Things like that, right? Binary addition is same. Signed, unsigned, same actually, right? You see point? So for microprocessor, they just do the simple binary addition or subtraction, something like this. But if you want, when you read each of the value, you can read it as a signed or unsigned or fractional numbers, if you like. Okay, if you like. Microprocessor don't care how to read it. So look at this operation, right? Look at this operation. It doesn't matter. Microprocessor doesn't know. MSB, if those two MSBs are 0, 0, and the output becomes 1. In this case, it's 1, right? Let's say these two are signed. Still the output is same. Let's say now we consider these two are unsigned. Still the output is same. Okay? You don't have to say unsigned or signed to do this binary addition. Binary addition is always like this. Doesn't matter, right? And microprocessor, if both of them are 0 but output is 1, I'm talking about only the first bit. Okay? If this happens, then it's overflow.
I wonder why we use the word overflow. I think it seems
Why do we use overflow?
Yeah, it seems like just carry, but we use overflow.
Good question. Why? Let's think about why. Okay, why do we need this flag? Why? Okay, that's a good question. Let's say we don't have this. Okay, let's say we don't have this overflow.
But I think just like there's a possibility we can use like if we want to result some kind of like negative value, then I think we need to use this. But like this is kind of like possibility. I mean, if we want to like get another the negative value, then this is like the possibility of using the kind of like the process. But if there is no process, I mean there is no like way to calculate the kinds of negative value, then that's kind of error.
Actually, I'm lost. I didn't understand fully what you said. But anyway, so what you're saying is that, what did you say?
This is another way.
Another way of doing what?
Because if there's overflow,
Uh-huh.
and if there's not overflow, then if there overflow flag exists, then we can use this one.
Yes.
But if there's no overflow, then we cannot use. So like the kinds of possibilities we can use this one, but like instead of this, we cannot calculate another value, which is negative value.
Actually, as he pointed out, the reason that we have overflow is to help you when you deal with the unsigned, when you deal with signed numbers. Let's say we don't have this, right? In that case, let's put it another way. Let's say we have this overflow. In that case, what happens? In that case, let's say we consider each one as a signed. Okay, let's say we have assigned numbers. Signed, okay? We have signed. So because of signed numbers, we are using signed numbers. This is a positive number. This is a positive number. And the result, we still use assigned numbers, right? So we are expecting to get the right value. For example, in this case, right? Let's say we consider as a signed number, signed. And now I have a value 64 in register A. I have 71 in register B. And I'm going to add these two. And the result, now go back to A. And I don't care what it is. I'm basically assuming that this A probably has the right value, which is this one. Okay? This is the right value, right? I'm expecting this value will be here. And then I continue do it. I continue do other calculation. However, since I said signed, in fact, this A is assigned, right? So when you read A actually have this value. A is no longer 135. It's like when you read it, it is read by minus some number, right? Minus 8, for example. So later calculation is all wrong. It's completely wrong, right? You see my point? Let's see here. Let's see the C. Basically, the same thing here. Let's think about C language. You know the C language, right? Let's write the C language. Character is 8-bit, right? Think about 8-bit. I define A. Let's say I have a signed 8-bit, A, B, C, D, something like this, right? And let's say I put A equal to 64, same example, B equal to 71, and C is A plus B. And what I'm going to do is, let's say I want to do D is C times 2, something like this. Let's say this is what I want to do, and I do the printf, and I want to do display. In this case, it's like a C, yeah, okay. Signed character still C, yeah. Anyway, so I want to print out C and also D, okay? You see my point, right? Maybe this is not the right context, but anyway, what I'm expecting is that when I read the value C, I'm expecting that C probably has 135 inside, okay? And I'm expecting that D have the value of this one. That's what I'm expecting. Naturally, right? Of course, that's what you do. But what you're saying is wrong. What you're thinking is wrong because we have 8 bits, right? And we define as assigned. Therefore, when you add these two, C, let's say 64 is this value, 71. What is 71? Plus 7. So it's like a 111, 1000. So this is 71. So when you add these two, right, you get the value of this one. You get the value of this one. That's what microprocessor does. Microprocessor will do binary addition. This is the value. But we define C as assigned. So when you read this, we read this as assigned. So therefore, it's not 135. Instead, we read this one as -8. Microprocessor do the same thing, but we read it, we define C as assigned. So therefore, when you read it, that becomes -8, not 135. So therefore, D is not this value, right? D probably is a -16. That's wrong. Nothing wrong in my program. I think nothing wrong, but actually it's wrong. So if you have no overflow flag, then I cannot correct this. But if you have an overflow flag, then what I'm going to do is that here, between here, I'm going to check if overflow flag is 1, then I'm doing another way. If overflow is 0, then please go on. That's what you do. Okay? So in order to check this condition, you need this flag. So basically the carry flag, auxiliary carry, overflow flag, all this flag is just to check. That's why we call it status, right? We just want to check the status, the condition. If overflow is on, then this kind of condition happens. So you need to be careful. You cannot just go on. You have to check it. Just for checking purpose. You see that? Okay? Yeah, so that's what. So important thing is you need to be able to see clearly when the carry flag is on and when overflow flag is on. And another important thing is this one, this one, this one. These three are independent, which means sometimes when you add these two numbers, these three can be all on. Sometimes, right? 1, 1, 1, all 1. It can happen. Okay? What is parity? Last one. It's not important, but the parity actually counts number of ones. Okay? So we have 8 bits here, right? You just simply count the number of ones. If you have all 0, then it's a 0. If you have 0, 1, 0, 0, 0, then we have only 1, right? 1, 1. In that case, it's 1. What if you have 2 ones? Like a 0, 1, 1, 0, 0, 0. So if we have an even number, 2, 4, or 0, then it's a 0. We have odd numbers, like only 1 or 3, 5, then it's 1. Okay? So parity flag basically check how many bits, how many ones in this register. That's parity flag.